Dear students, welcome to the knowledge series. Here we will be discussing on the continuations of genetic algorithms. I believe that you have gone through my previous video series on genetic algorithm. So this is in continuation to that video series. Here we are going to discuss on the motivations of genetic algorithm. As you can see, the statement it states that the genetic algorithm works in the principle of survival of fittest. These particular terms, as you all know, Charles Robert Darwin, he stated way back in 1837 to 39 during his work, and the book which he has published in the year 1859, there he specifies this particular statement in his book on the origin of species. Survival of fittest among the string structure and search algorithm in randomized. String structure is nothing but the bits that we use to create the chromosome. That is what we have already discussed the terminology, and that chromosome is the one which we try to further go with the populations terms, and that creations of the chromosome or the selection of the chromosomes and the appropriate populations search through the search algorithm is carried out in a randomized way. Now, why this randomized way of search is being carried out, as I have already stated, is that in the case of a gradient descent methods, we try to look for the global minima or a global maxima. Accordingly, whichever is suited for our applications, according to that one, we try to look for the best of the maxima or a best of the minima. Now here, the important of the genetic algorithm, it is stated that random search technique. The chromosomes are selected randomly without any conditions, because when we initialize the search, we have to start with the initial conditions, and that initial conditions, it is better if we don't know the exact solutions. At least we can start with the random search, or in a randomly selecting certain values. We have to start from there, and thereby we have to check at the end of every iterations what is the results. The second point is the suitable for parallel processing. Due to this, we can get optimal solutions with less times. That means genetic algorithms is suitable for a high-end computation. So that's why, because of the existence of the computers with the parallel processing systems, we can able to carry out this search in a easy way. So that is optimal solutions we can obtain in a short time. This can be used in a noise fitness functions. So based on the wherever we are having a different type of variations, in the variations we can try to identify the best fitness functions by neglecting whichever the noise is being created in that particular bits level. It is simple to develop. When I say simple to develop, it does not mean that it is so simple, but it is the process and the algorithm is well defined, so it is easy to develop. Genetic algorithm will produce a close to optimal results in a reasonable time. So that means it is genetic algorithm is a search based. So as we have been using that particular term, that it is a search based technique, so that's why we will be able to find the solutions that is the best solution in a reasonable time. Probability of a randomness are essential part of the genetic algorithm. So when we talk about a randomness, that randomness and the probability and randomness are closer proximity in the case of a genetic algorithms. They are adaptive and learn from the environment. That means the adaptations and finding the error, mean square error, and further going for that error corrections, as we have seen in the neural network. In the same way, they are adaptive, and they can able to learn from the environments. They can able to improvise based on the feedback conditions. Chromosomes are important that contain in the genetic informations. As I have already stated that chromosome in the case of the genetic algorithm, it is one such solutions that gives for the any problem based on the genetic algorithms attributes. Now, with this important information, what we mentioned, random search is the parallel processing for a fast computations, identifying the unwanted genes or the bits, and optimizing that one in a faster basis, and knowing that probability and randomness is closeness, this can be able to produce in an adaptive manner. If you go and look at this particular figure, you can see in the x-axis is a parameters is being given. You can see that these are the parameters that we are looking for. That is our objective or the goals, and in that goal we are doing that objective functional values. That means we are doing a corrections based on these values. That means with this value, if we do the corrections, we can attain to these parameters. So genetic algorithms have the ability to deliver good enough solutions with a fast convergence, or it can have a good enough solution to the fast solutions. Now, if you see the solutions, how it is going to produce, that means every time it goes, whether it looks for the maxima, if these are the maxima, then you go from the, you try to look a upward trend and try to see that how you can adjust the weight or adjust the attributes, and based on the adjusting the attributes, attribute maybe in the form of a chromosomes or in the form of a genes level, you can do this adjustment, and there how you can able to attain the corresponding maxima or minima. Now these genetic algorithms, it is an efficient tools that provides a usable and a near optimal solutions in a short amount of time. Now in the real world, we have enough complex problem, and that suffer from the inherent factors, and that factors, if we can apply make a visual study through the gradient descent method, we will be able to analyze how we can able to solve this particular problem. And moreover, if you do the hardware implementations using VLSI designs, we can able to have a good solutions at a faster rates. So that's how this particular genetic algorithms motivation is being reflecting towards the development and better outcome of the any problem. Now we go further. You may be recalling that we have talked about a genotype and a phenotype, and in the genotype, what we have discussed is that it is populations in a computational space, and that computational in a computational space, we try to put in a phenotype, and that phenotype is the population in the actual real world solution space. So that is what we have already discussed, and you have also have gone through my my previous slides where I talked about the populations and I talked about the chromosomes and the gene. So in a simple word, a population, if you take our country, that is a populations, Indian population, then we take our states, that is a chromosomes. And inside a state, every district is nothing but our gene. So like that, we distribute the terminology for understanding. Now we look forward in the genotype representation. In the genotype representations, we have shown here some of the representation. Let's start with the genotype representations one by one. Now, why we go for a genotype? One of the important decision for implementing implementing a genetic algorithm is to represent our solutions. And to represent these particular solutions, we have to properly map our problem to the phenotype and the genotype space. That is very important. And once we map this phenotype and genotype to this particular space, so we can able to have a specific solutions to that problem. So such representations in a highly complex problem, it can able to give solutions based on the conditions, how that particular problem is alike. If it is a more complex, then we have to go for a number of steps. If it is a less complex, then you have to reduce that steps accordingly. Now let's start with the binary representation. If you see the binary representation, it is represented in terms of a 0 and 1. And this is considered as one of the simplest and most widely used representations in the genetic algorithms, because such type of representation in the genotype we represent in terms of zeros and 1. That is what we have stated. And of course, if there is n bits are there, then we have to represent in terms of n bit representations. Now we go to the real valued representations. Now in the real valued presentations, it defines in terms of discrete variables. And you know the real valued representations in this discrete variable is most natural. And the precision of a real valued or a floating numbers is, however, limited in a computer. So that's why in the computer representations case there is an issues. Otherwise, this type of representation of a gene, because this is a bit level, every bit is a gene, you should take it. So this type of representations is natural, but there is a constraint is also there. Integer. Now, if you look across a discrete valued genes, we cannot put it in terms of a yes or no in the binary space like a 0 and 1. So if you want to represent in terms of a representation as a 1, 2, 3, 4, that means if you are having a 4 different conditions, and that 4 different condition has to encode. So we can represent 1, 2, 3, 4, 3, 2, 4, 1, 2, 1, like that we can able to represent. Say for example, east, west, north, south, then like that we can represent in a different zone. So depending upon the x, y, north, south, east and west directions. Now there is another way is that in many problem the solutions we find that we have to represent in terms of a permutation representations. So under such conditions we can represent this one having a value 0 to 9. So that's how we can able to represent in this one. Because here if you try to do the real valued 0, here it is representing from 0.1 to 0.9. So that is how it is. Now here we can represent from 0 to 9 in a permutation representations conditions. Like for example in the traveling salesman's problem. So we where the salesman has to move to various cities, and try to see that how he can make the shortest movement, and also and he can visit exactly to those cities only once and come back to the starting point. So all these conditions we needed a permutations condition. So the permutation representations we represent in this order. Now here there is a very another important. We have discussed the optimizations conditions. So the constraint of the optimizations problem between the input and output is to go for improvement. So under the case of the constraint optimizations problem, the optimizations conditions, what we do, either we go for improving this optimization to a maximum or for minimizing. That is our objective, because when we do for optimizations, we have either we have to go for the plus side, or we are looking for the minus side. Whatever terms we are doing, we are taking, that is the objective functions. So if it is a maximizing or minimizing of the objective function under the subject, so these constraint optimizations we are defining in terms of a feasible region and an infeasible region. So the solution space, what you can see over here, this is a feasible space. So that in that space, if there is a infeasible solutions exist, so we have to see that how this particular constraint conditions we can able to optimize. So some of the condition is that if you have any noise existence, so we have to we have to reduce that particular noise, so that the fitness functions of the infeasible solutions can be reduced by giving applying a penalty functions. So that is what we can do in the infeasible solutions. If the fitness function exists, so we have to create a penalty, so that this should not increase. So on the other hand, we should try to repair these functions of the infeasible solutions, and we have to see that we will not allow the infeasible solution to enter into all the into the populations at all. It is just like you think about this is a space populations, and this is the region which is a protected regions, and this is the space where a corona red zone is being detected. So this red, this is assume that this is a protected zone and green zone. So this red zone, if people should not enter into this space or to this space, so so that it should not create the virus to spread into the unrestricted zones, or the zone which is free from the corona disease. So that is how we have to see. So we have to, what we have to do, we have to go for the correction of these infeasible solutions, either in terms of a penalty functions for violating the conditions, or by treating that particular functions by repairing it, or not allowing the functions to mix with another populations, or other regions of the flexible areas or flexible regions. So such type of representations needs what all the above representations, genotype or a phenotype, to take a study. That's how we can able to control the optimizations problem. Now we are entering into the very important discussions with respect to the genetic algorithm basic block diagram. Now here some of the genetic block diagram flow block diagrams, I can put it as it is being represented, and those block diagram is very important for you to understand what exactly the flow diagram is representing. Now the very first things, if you can try to see the populations. we are trying to go with the first phase is that we are creating a population initializations in the genetic algorithm flow diagram. Now the populations is the collections of the chromosomes that you are aware about it. Now after collecting the initial populations, what we are going to do is that we have to find the fitness functions. That is a fitness of this population. Now this is a fitness functions calculation, and the fitness functions, it determines how fit an individuals as it gives the fitness score of an individuals. So from here we get the fitness score of these individuals. Now once we find the fitness score, so we are going to classify that or group that particular individuals so that it can be ready for the next stage. Now the next stage is nothing but a crossover. Now in the crossover, what we are going to do is then we are taking two parents and two chromosomes in that parents, and going to have apply the crossover. From the crossover, there is a different stages are there. How we are doing this particular crossover point, and once the crossover is been completed, then it is going for a mutations. Where when the mutation occurs, what we are going to do is that we are going to find we are going to maintain the diversity of these populations, and to prevent from a premature convergence. You have that means if you see this gradient descent method, we are improving, but it should not happen that we are returning back. Then that time the results is going to inferior, and it is wasting that much computational times, etc. So that should not happen. So in the mutations, it occurs to maintain the diversity within the populations and prevent from a premature convergence. That is very important you to understand. How it is going to happen, that we'll discuss. And next what we do, we try to determine which individuals are to be kicked out and which are to be kept in the next generations. That means here we are going to look for the best chromosome and try to remove the one which is not fittest one, and then we follow the similar path. Why we follow this one, the loop until termination? Because we are following this path because we are looking for a local minima or local maxima based on the gradient descent. So we have to achieve that one. So till that time we continue, and finally after verifications whether the value after the mutation is getting same always, if it is so, we are going to terminate. So this is what is the basic structure. So you have to understand populations, initialization, then we go for a fitness. Then once we go for a fitness, after that what we do, then there is a 3 stages coming. This 3 stages is for creating a new populations, that is a crossover, mutation and survivor selections. Once this 3 stages is completed, the new population is again coming back, again its fitness function is carried out, then again new population is created, again it goes like that. We continue, and this continuations process will go until we reach to the objective of our problem, and thereby we terminate. This is what it is being shown here. If you can see this block diagram for a while. Now here, if you see, it is the same thing exactly like this one. Start, initialize populations, and from there we calculate the fitness. Fitness of what? In these populations, the several chromosomes are there, X1, X2 up to XN. So their fitness is what we find, and after that then we go for the creation of the new populations, and that new populations whether is it that population is this chromosome is sufficient for us to give the solution or not. If it is not, then we go for a new parent selections based on selection, crossover, and mutations. So that means crossover, mutations, selection is already carried out. So this has trying to give a new solution. That's how we continue. This process will continue. Selection, crossover, mutation, selection, crossover, mutation, like that. And finally, if everything is okay, then it is going to terminate. So we will discuss with respect to these particular individuals one by one. So let's see over here. The first is population initializations. Now, what exactly the population initializations indicates, that is very important for us to understand. So the population initializations means we are going to discuss with respect to the first is nothing but a gene, individual bits, chromosome, the complete collection of bits, and population, collection of chromosomes. So here in the population initializations, it is two types. One is random initializations, another is heuristic initializations. And you know that in the case of random initializations, we try to go for initial initializations with a completely random solution. So randomly we take the value and go for initializations of this one. Now the second is a heuristic initialization. Heuristic initializations is nothing but based on the previous values or the previous data, we can try to analyze that, okay, this is the result. So based on that, we try to apply the heuristic approach and try to find the solution. So that is known as a heuristic methods of solution. Now this is, you have to understand, this is randomly selected. This is selected based on the previous value. So that means based on previous value means it is not a random, but having some awareness. So the probability in this case is better as compared to this. The next case is a populations model. And one more point with respect to this one here, that it has been experimentally observed that the random solutions are the one of the popularly known solutions for the optimizations. And therefore, with the heuristic initializations, we need the populations information for getting a good solutions. If we don't have a data, then we have to go for a randomized solutions to fill that particular gap. Now, if you look across the populations model, there are two types of a populations model is given: steady state and generational. Steady state means we have a one or two offspring. Offspring is nothing but a creation of a child after each iterations, and this is replaced by one or two individuals of the populations. That means in the case of a steady state, whatever is the previous population's chromosome is there, that will be replaced by the new offsprings, and thereby you will be getting a better results. So that's a steady state genetic algorithms is also known as incremental genetic algorithm, because it always creates a new population, but it also has the old populations with them. So the old information and the new information work together collectively, so that it will give a better scope of improvement. Another is generational. In a generational model, we generate n offsprings, where the n is actually a population size, and the entire population is replaced by the new one at the end of the iterations. So this is different as compared to this one. So here the entire population is replaced, whereas in this case it is not replacing the entire population. It is taking the previous populations, and with the new offspring it is working together. So that is what we see in this case. So here the possibility of reaching to the global maxima and minima will find a better solutions as compared to the generational type. Sometime it may fail, sometime it will produce, but there is no certainty in that conditions. Now next we go for the fitness functions. Now let's see these fitness functions, what exactly it is. Now the fitness functions, it talks about the how a particular candidate solution to the problem as an input will produce a fit output, or we say that a good solutions with respect to the problem under that particular condition. So calculating a fitness is basically one of the important components once the population is been selected. So when we talk about a fitness conditions, fitness, there are some method is there that will give a fitness score. So here in this one, if you can see, this is item number, and this is the chromosome, this is the profit value, weight value. So there is a knapsack 15, total associated weight is 18, last item not picked, it exceeds the knapsack capacity. We use this one as an example. We will be discussing this example to understand how we are using this fitness function. So in the case of fitness functions, what we try to see is that every time we try to do a comparisons with respect to the bit level chromosomes with the set value. If it is exceeding or is it below? If it is exceeding the range, and if it is not meeting the needs, then we are going to consider it as an unfit. And if it is below the range, we are considering it as a fit chromosome for the next iterations. That's how we continue, and every time we are looking for a fit value. That is what in the case of a knapsack it is being done. So a fitness functions has a certain criterion. One is that it should be sufficiently fast to compute. Second thing, it should be quantitatively measures how fit it to a given solution, and how it can produce the solutions further using that fitness values. So if fitness function is not correctly evaluated, then the complexity will increase. That is, the inherent complexity will increase. Thereby you will not able to attain the global minima or global maxima. So that particular situations will need to be overcome, and that particular solutions, if it is not overcome, so what will happen? The iteration will keep on continuing, and the system will not able to achieve the final optimizations results because of the global minima and local minima, global minima, local minima, or global maxima, local maxima attainment if it is not able to reach. So these are the point with respect to the fitness functions. Now we go to the parent selections. Now parent selection is the very important components where you have seen that what are the methods we have been using. Now parent selection, it is the process of selecting the parents which mates and recombines to create a new offspring for the next generation. That is, we are going for a 2 chromosome to select. And parent selection is basically very crucial for the convergence of the genetic algorithms. So that is what I have been stating, is that if you want to achieve the solutions, then the gradient descent methods should able to attain in a appropriate way. So that is gradient descent methods should make the solutions to reach based on the proper selections of the parents and its iterations. Now, if you look across the parent selection, the fitness proportionate selection, that is nothing but an operator. So how you select the operators for the fitness proportionate solutions. Now here in the fitness proportionate solutions, the probability of the fitness functions is being considered for those populations to go for crossover. So that is what plays very important challenges. So therefore the fitter individuals or the fitness chromosomes have a higher chance for mating and propagating their futures for the next generations. So that is what you have to keep it in your mind. Therefore such a selection strategies applies for the individual populations to go for the crossover. Now here how will you select the parents? Of course you have checked the fitness. Based on the fitness value you have identified the particular populations, but does it remain same? In the populations we have to look for the best population. So what we do is that we will use a roulette wheel. Roulette wheel is something like that, and we spun this roulette wheel, and once we spun this roulette wheel, and this roulette wheel will keep on rotating, and in the circular wheel where you can see a fixed point. Now in this fixed point when the roulette wheel rotate, automatically a wheel circumference automatically come to stay across the fixed point for a certain while. So here you can see the yellow sector is which is in the at the point of the at the fixed point zone. So so this zone area you can see, whereas suppose if you see the blue, it is a large. If you look at sky blue, it is still large, whereas if you see green, it is very small. So the what we do is that a region of the wheel which comes in front of the fixed point is chosen as a parents, and this we continue. Which the region which is more the region which bigger region which is coming in front of the fixed point for a more period, that is what we select as the fixed fitness values. So here we see the fitness value here. How we see the fitness value? A, B, C, D, E, A. So once we spin this one, we will be choosing the parents accordingly. So if this is A, then its fitness value is 8.2. If it is a B, it is 3.2. Like that we can able to calculate. And if you sum all this one, we get the total fitness value sum. So and based on that you can calculate the mean value you can go for a mean value or a average values or a maximum values. Like that we can calculate the computations. Now another is a stochastic universal sampling. In a stochastic universal sampling, it is similar to the roulette wheel solutions. However, instead of having a one fixed point, we will be having a two fixed point. So if you have a multiple fixed point, you can able to create a similar form of a fitness value. So you will rotate this one, and based on that you will be selecting the two different points, or you make a certain conditions with respect to the two fixed point, and you create a function. Now in you can note that the fitness proportionate selections methods actually it did not work, whereas such type of fitness function can take a negative values. So that is the one which is observed in the case of a stochastic. And compared to the roulette wheel, there is another selections method, is that if we go with the what we call as a tournament selections. Now in this case of a tournament selections, you can see this one is that in the case of here there are a fitness values is being given. So this is let us take this one as a k individuals. You are having a individual chromosomes is being shown, and its fitness value is being considered. And just like we go for a tournament selections of extremely popular groups, how we do, we will take the individual fitness value. Like if you take in the cricket teams, we want to take a best player. So what we'll do, we go with the Ranji Trophy in the state wise, and from the state wise Ranji Trophy, then we go for from the state state to state, we go for a next tournament, and finally we go for a selecting the best selections from the various state. That's how we try to get the best players. In the same way, here also is that one group is being selected, and we formed a from this group E, then from this group we got T. So select a K chromosome at a random way, and from there we try to find the fittest of this one. So this is just like a tournament selections. Another is a random selection. So in this particular form of random selection strategies, what we select the parents from the existing populations, and no selection process is being done. And so and we consider them for the fittest, and that's how we use it for going for the crossover and mutations. That's how we try to see that that particular parents is being considered as a fit under the case of a random selections. Now we go with the next is a rank selections. You can see in the case of a rank selections, what we try to see that we select the chromosome based on the roulette wheel conditions, and we find the fittest values. So so we write ABCD chromosome, and which is having a fittest value, we will write it. Among this fittest value, we will put the order. This is 1, and then we'd go 2, like that, 1, 3, 4, 5, 6, and the least one is the largest value number of rank. So this rank rank order is being created in the fitness value, and thereby we will select the parents for the mating purpose. So this is the basic criterion for selections of the parents. So the next point of our discussion is with respect to the crossover. So in the crossover conditions, we are having a selections. We can do a crossover like this is a chromosomes. We can this is the two chromosomes we are taking, and we are going for mating condition. Under this mating condition, we create a crossover point. In this one, the bits are interchanged. That is what it is being shown. The pins are interchanged, and the new offspring what is generated, it is 111000 and 001111. So this is the new offspring which is being generated after A1 and A2 is being met. So there are different type of a crossover. So one crossover is a 1 point crossover. That means we are interchanging the values on one side. So that means we are keeping this one as standstill, and these bits are interchanged with this. That is known as a single point crossover. You can see this is green is standstill. Here 549 and 2 is standstill. Right side is interchange. So that is what we see. This green has come to this side, this blue has gone to that side. Now another case is a multi-point. In the multi-point, what we do is that now we go for a 2 point crossover. So here is a 2 point crossover. We take a 2 region, 2 crossover point, And here you can see from the color is that this middle region has interchanged. 423 and 345 is interchanged. That is known as a 2-point crossover or multi-point. Uniform point of a crossover. So in the uniform point of a crossover, what we do is then we select certain bits. Say for example, here if you take this bit here in the we change between the 0, then we go for a 2 3, then we go for a 6, then we go for a 8. These bits are interchanged, so this is known as uniform crossover point. Then we go with the arithmetical recombination. In the arithmetical recombinations, what we do is that we take one functions, and based on that functions we try to put the value, and we try to generate the solutions. That means if you look across this one, 0.1, 0.1, this is the range up to 0.5. So this particular point is being selected, and from this particular point, new child is being created based on the functional value, based on the function. Say child 1 is equal to say alpha x plus 1 minus alpha y. So based on that child 1, and another is child 2 is being created based on that 2 values. So that's how we will be creating the 2 value. Or we try to stake this one, say 0.5 and 0.7, 0.5 and 0.2, that is total divided by 2. So we are getting a new parents 0.35. So that's how. Or 0.5 and 0.3, so 0.2. So we get we created based on that function. Or 0.1 and 0.2, 0.3, so divided by 2, 0.15. So that's how also we can able to. So we use arithmetical recombination on the function. So here in this figure we have taken x this plus this divided by 2. That's how. Now another is a Davis order crossover. In the Davis order crossover function is what we are going to do is that we this particular crossover is with the intention of transmitting the informations to the relative order of the offspring. That is what we do in this particular case. Now if you see it carefully, in this case this particular 3 4 5 6, that is being considered for the midpoint selections, and here the unused bits, the unused bit is being considered. Now this is already occupied, the 1 point. Now in the unused bit, what is the bits? If you see 281 is not being used, so that is one side. 970, that is not being used. So this is the new generations that is being used with respect to from these two we are filling these two. From these two we are selecting one middle bit. Say from these two we are taken this one as a middle. From these two we are going to create the unused point of filling these and these regions. So if you see this one, we have got 281 across this place, and 970 we have got it on the other side. So like this one, there exists a lot of other crossover, like a partial mapped crossover, or a order based crossover, shuffle crossover, a ring crossover. Like that, many crossover are still existing. Next is the we discuss about the mutations. And in the mutations, what we do is that in this particular case, as I have already shared in my previous point, is that why we go for a mutation. We try to see that it can able to produce a better performance with respect to the results. It should not happen that after doing a particular mutations, your things will be going back instead of improving. So mutation is basically is to occur or maintain a diversity within the population, and it prevents from the premature convergence. So that is very important. So what are the different mutations methods is that one is here you see 1110000. So what we have done, we have muted this one, these three things, these three. This 1 becomes 0, 0 become 1, this is 1. So this is after mutation, before mutation. So there are different mutation, bitwise flip. So we only change this bit. 1 becomes 0, remaining is same. Or we go for a random mutation. We take a random resetting of the bits, flips, or the integer representations if it is integer type. So in this way we can, in the random value, a set of permissible bit values are randomly chosen for the genes interchange. Swap mutation. So you are swapping between 2 and 6. That is not scramble. So you are selecting a certain bits level, and that one is you are scrambling in a randomized way. Say 3, 6, 4, 2, 5, and our same thing is there in 2, 3, 4, 5, 6. Inversion mutations. So you are changing the positions of the bits. 2 become here, 3 become here, 4 remains same. So that is known as the mutations methods. Now next we go for a survivor selections. Now in the survivor selections, what we do, we try to see the age-wise and the fitness-wise. Age-wise selection is nothing but we select age and its fitness value and its chromosome. So that chromosomes, say among this one the fitness value 8 is taken, and among this one the fitness value 9 is there. So the best fitness value is taken 8 and 9. So those fitness value is being combined together and try to create a new chromosome. So if you try to see 8 fitness value, so this has come, C1 has come here, and the next fitness value C2 has come here. So this becomes the new offspring's value. So this is how we try to create the new. But here one thing you observe, this one is the young one. So the lower fitness value is being getting the modified one. So the improvement one you are getting over here. So that is the one things you can see in the offsprings. Now here the another method is that in the offspring case, one more point you can see over here, the fitness value, the second case is the high value. So that high value fitness value is being brought here. Now here the fitness based selections, so this is age based. So in the age based selections we try to look for the so which is having a maximum age is being considered. Okay, now here with respect to the fitness value we will check it. So we find that the fitness value 1 and 0, this is the low fitness value. So we have got a fitness value 8 and 9, and this is the new offspring. So this offspring will replace this population. This is a population. So this is the new populations which has come 8 and 9. So this is how the new populations is being identified with respect to the survivor selection. So whichever is not going to sustain for a longer time, it will be replaced. So this age is not sustaining, so it is replaced, and this fitness is not able to survive, so this is also replaced. So that's how we come to the final conclusion of a termination. And the termination condition in a genetic algorithm, basically it is an important for determining how long the genetic algorithm need to run. So if it has to be observed, then we have to see that how genetic algorithm can look for faster solutions and better solutions with a minimum iterations, and this particular trend should try to see that there is an improvement in the solutions, not that it keeps on continuing. So that's why here it is, when there has been no improvement in the populations for X iterations. But that means after a particular iterations, when you are finding that even after doing a mutations, there is no change in the output results, then you can able to terminate. Or you have attained to the objectives, or absolute number of generations you have attained it, then only. then you can terminate, or the objective functions you have attained, thereby you can able to terminate. So these are the different methods, thereby you can able to see that with the new populations you are creating a new offsprings, and thereby you are going for improvement, and try to see that optimization is taking place. And if this particular process if it is not able to give a further change in the output results, then we feel that then we can understand that it is the time for genetic algorithms to terminate that particular process. Thereby you can able to consider that the output result is optimized under that particular given input attributes. So with this we stop here with respect to the very basic and very important discussions on the genetic algorithm flowchart, and in the next discussions we will discuss about the further study and the numerical problem.